Okay, it's lesson 16, and lesson 16 takes the chain rule and brings it into an area where we are oh so very comfortable, geometry. Because geometry for the win. What we do in this lesson is we look at rates that are related. And so these are traditionally referred to as related rates problems. They are not named for a person named related rates. They are called related rates problems because they are problems about rates that are connected to each other in some way. There is a nice recipe for solving problems like this. This is the thing that goes on the index card. This is the thing that you commit to some sort of memory, either by straight out memorizing or by doing a bunch of questions until you have this process down. You want to draw a picture. You want to write down the information that you're given. You want to write down what you're asked to find. You want to write the equation that relates the variables. You want to take derivatives with respect to time, and then you want to evaluate at the end. Now, I'll come back to these ideas repeatedly. I'm going to do 4 examples, and for each of the examples, we're going to run through these 6 steps, because if you do these 6 steps, you can't go wrong. When you think you've got the process right, you can stop watching. Here's example 1. Air is entering a spherical balloon, 10 centimeters cubed per second. At what rate is the radius increasing when r equals 5 centimeters? Step 1 is to draw a picture. In that picture, you have a sphere. This is a sphere. It has some radius. Step 2, we're supposed to identify what information we are given. So step 2 says air is blowing into the balloon at 10 cubic centimeters per second. Well, that's a rate. Rates are derivatives. What is changing with respect to what? Well, cubic centimeters, that's how we measure volume, and seconds, that's how we measure time. This is volume, this is time. So this rate is a derivative of volume with respect to time. That is 10. It is positive 10 because the balloon is increasing in volume at 10 cubic centimeters every second. So step 3 says we're supposed to talk about what we need. Well, what do we need? At what rate the radius is increasing. We need to know at what rate the radius is increasing when the radius is 5. Because dr dt will depend on r, and so we want to know what dr dt is when r is 5. So let's see. We did this, we did this, we did this. Relate the variables. So what is the formula that relates volume to radius? Well, the volume of a sphere is 4/3 pi r cubed. That's the equation that relates the variables. Volume, radius. V equals 4/3 pi r cubed. So then step 5 says we're supposed to differentiate both sides with respect to time. Now, that's not time, and that's not time. You don't see time anywhere. This is where chain rule kicks in. The derivative of volume with respect to time is the derivative of volume with respect to time. And the derivative of this thing, so if we were just taking the derivative of this thing like normal, power rule 3 comes down, that's a 4 pi r squared, but this is the derivative with respect to r, and we want the derivative with respect to t, so we multiply by dr dt. This is the only calculus we do in the whole problem. This is interpreting, this is interpreting, this is geometry. This is the only calculus that we do in the whole video. Well, in this whole example in the video. So we plug in all the information that we have. dv dt is 10. r at this key moment is 5, and we're looking for dr dt. So at what rate is the radius increasing? Well, that's 10 divided by 100 pi, and that's in centimeters per second. That's dr dt. I will throw a few more examples our way. A 10-foot ladder is leaning against a house. Here's the 10-foot ladder. The bottom of the ladder is kicked out at the rate of 1 foot per second. Well, how do we say that? Well, once the base of the ladder starts moving, this distance changes, this distance changes. We're just going to assume that the house is built decently. So when we say that the bottom of the ladder is kicked out at the rate of 1 foot per second, that means that x is growing at 1 foot per second. That's the information that we're given. So what are we supposed to find? We're supposed to find at what rate the top of the ladder is falling down the wall. We're supposed to find out how this is changing. We need dy dt when the base of the ladder is 6 feet away from the base of the wall. So we know what's happening to x. We want to know what's happening to y when x is 6. Step 4 is to relate the variables. What is the relationship between x and y? Well, that's Pythagorean theorem. The Pythagorean theorem is what relates x and y. Notice that the size of the ladder ends up mattering because this 10 turns into that 100. So step 5 says, what are we supposed to do? We're supposed to take the derivatives on both sides with respect to time. So the derivative of x squared is 2x, but that's the derivative with respect to x. We want the derivative with respect to time. The derivative of y squared would apparently be 2y, but that's the derivative with respect to y. We want the derivative with respect to time. And the derivative of a number is always 0. So then we put all the information that we have into our equation. Step 6 talks about evaluating. Well, what are all our pieces of information? We want to know when the base of the ladder is 6 feet away from the base of the wall. X is 6. We know what dx dt is. That's 1. We know what y is when x is 6 because we know the Pythagorean theorem. And then we don't know what dy dt is, so we find it. So dy dt is negative 12 over 16. That's negative 3/4. What's the rate on that? Feet per second. We measure y in feet. We measure t in seconds. So the rate is negative 3/4 feet per second. This makes sense. It makes sense that this is a negative number because y is decreasing. So dy dt should be negative. 2 more examples I'll move a little bit faster through. So Jimmy is running from first base to second base on a standard baseball diamond where that's 90 feet. That's home plate. He is running at 20 feet per second. Running at 20 feet per second, which means that this is growing at 20 feet per second. So if this is Jimmy, the poor picture of Jimmy and that poor leg there, this is a distance that changes over time. This distance is always 90 feet. This is a distance that changes over time. So this distance changes, this distance changes, this is always 90 feet. So Jimmy is running at 20 feet per second, which means that this x is growing at 20 feet per second. we want to know at what rate is his distance from home plate changing. We need dy dt when he is 30 feet from second base. Well, if he's 30 feet from second base, then he's 60 feet away from first base. And we look at this right triangle and we relate the variables. X squared plus 90 squared is y squared. And then we take derivatives on both sides with respect to time. You should ask yourself why there are 3 terms here, but only 2 terms there. That's a question worth asking. We make the plug-ins. Oh, how are we going to figure out why? How are we going to figure out why? Well, at the moment in question, that's 60, that's 90, that's the square root of 60 squared plus 90 squared. Well, how the heck much is that? Well, that's 8,100 and 3,600. That's what, a square root of 11,700? So what's dy dt? Dy dt is 60 times 20 divided by the square root of 11,700. That's in feet per second because we measure y in feet and t in seconds. And there's your, oh, sorry about that. There's your change in y. One more. A rocket is rising vertically from flat ground at 20 kilometers per minute. Well, what does that mean? Oh boy. So what does that mean? If the rocket is rising vertically at 20 kilometers per minute, well, that means that this height is changing, and the height is changing at 20 kilometers per minute. There's a camera that's 6 kilometers away from the launch point, and it's always watching the rocket. So we're talking about the angle of elevation and how that is changing when the rocket is 8 kilometers off the ground. This is the thing we're looking for. We need the rate at which the angle of elevation is changing when the rocket is 8 kilometers off the ground. So we need a relationship between h and theta. And, well, that's tangent. That's tangent. In fact, h is 6 tan theta. And so then what do? Well, we take the derivatives on both sides with respect to time. The derivative of the tangent of something is secant squared of that something. Chain rule. The derivative of h with respect to time is the derivative of h with respect to time. So now it's time to figure out what all of our things are. We're looking for d theta dt. We know what dh dt is. And so how do we figure out secant squared theta? Well, at the moment in question, that's 6 kilometers. That's 8 kilometers. This is the moment in question. Secant. Secant of theta is this over that. We don't know what this is. Oh, wait, we do. That's 6, 8, 10. So the secant is 10/6. And then you can figure out what d theta dt is. It's not terribly difficult. So you got a 20 here. That's 5/3 squared. And then this comes over, and I imagine that this simplifies, but whatever that number is in radians per minute. And that's some related rates questions. When we come together, I'll have more for us to practice with. For now, you should just make yourself familiar with the process. Can you follow the process through the 4 examples? We'll take questions on that when we gather in class.